Hey everybody. I think the screen's not that big. My side's a little small. You might want to kind of gather in a little bit here. Hi, I am Alan C. Smith, certified LabVIEW architect, embedded developer, CPI, LabVIEW champion, and I make my living as a consulting software architect. I've been writing LabVIEW code for over 30 years. So yes, I was at NI for a little while, but Nancy, I was just doing what I always do, and NI happened to be paying me at that point. Yeah, I've done it all. I've been a partner. I am a partner now. I've worked for partners. This LabVIEW has been my life, my professional life. Those of you who know me know I love me some classes in my applications. I've been doing class-based object-oriented design since about 2005, which actually predates when we got them in LabVIEW by about a year. We've had classes in LabVIEW since 2006. Quick show of hands. I can't see past the lights. Who routinely uses classes in their applications? As I would expect, this room is pretty much bought in, as is most of the community. After a slow initial adoption period, it really took off, and just checking in with my friends in NITSE, I know that most of the applications they see have at least some classes. Many of them are, extensive object-oriented designs. It probably surprises no one here that LabVIEW is just everywhere. Our two largest frameworks in LabVIEW, Active Framework and DQMH, are both built with classes. DQMH hides that from you because they want to be friendly to folks who aren't so invested in classes. Active Framework assumes that you're fully bought in, but both of the frameworks under the hood run off of classes. And in fact, LabVIEW itself, the parts that are built in LabVIEW, often involve classes. We talk about this in the OO course. This is our friendly splash screen that we see every time we start work, and it is all classes under the hood. Okay, so classes are here to stay. They're a part of the language, and ideally everyone would embrace them. But if you haven't, so this presentation is probably targeted at a slightly different group, because if you're new to LabVIEW, if you're new to the idea of object-oriented development, or have been doing it for a long, long time in a more traditional fashion, you may not be as interested. And I get it. I truly do. This is the project file for a project I've been working on for a customer off and on for 6 years, and it's a wall of classes. And if you're not used to that, if you're not used to classes in your development environment, you're looking at that, that's a little intimidating. Object-oriented programming in LabVIEW, writing classes, is easy, right? I can teach you to do that in an afternoon. Object-oriented design, on the other hand, that's more of a hurdle. That takes often, if you've started doing it, great, but if you started off doing it different ways, that's a transition that you have to go through, and it's an investment that some organizations haven't wanted to make, or some people might be looking at and go, oh, I don't know if I want to do that. So our advice in the class is to start small. And the good news is you can stay small. And that's what this presentation is about. This is going to be targeted at the few of you who maybe haven't bought into classes yet but are curious. For those of you who are representatives of organizations with junior team members who are like, what are these objects? How do I use them? Refer them back to the recording from this, or take this presentation back to them and use it to help them. That's my target audience for this. Because I'm going to talk about a few simple design patterns that I use all the time, that you can use in isolation, so you don't have to use them with other classes necessarily, so you're not doing a whole OO design, but you can drop these into your traditional LabVIEW code and get immediate benefit. Start using it right away. Start seeing an improvement to your overall code quality, your ability to read your code, your ability to test your code, and so on. You can drop them into something like this. Now, I'm talking about design patterns, and we often mistakenly refer to this as a LabVIEW design pattern. This is, of course, our old, very old dear friend, the queued message handler, which, you know, Active Framework and DQMH are queued message handlers under the hood. It's been around for a long, long time. We love it. But it's not really a design pattern. This is a LabVIEW implementation of an idea, and that idea is to have some sort of message dispatcher where I have an independent thread getting messages and doing things. Okay, that idea is a lot closer to the concept of a design pattern. In software, we first started talking about design patterns with this book, Elements of Reusable Object-Oriented Software by the Gang of Four. This is a great reference. If you're doing class-based design, you should have this book or something similar to it on your desk. Interesting bit of fact, since apparently Scotland is like a major, if you're an architect geek, you like to come to Scotland, they got the idea for design patterns from structural architecture. They stole it and applied it to software. And it's just the idea is that we just have these ways of doing things that we do over and over and over and over and over again in software in all kinds of applications. They're not application specific. It's not a piece of code I can hand you. It's an idea for how to organize parts of your code to solve certain specific problems. That's a design pattern. And I'm going to talk about, I'll talk about these four: aggregation, state, template method, and then factory method is not actually one I would recommend you start with, but I'm going to mention it because it's a place we often wind up, so I kind of want you to know that it might be coming for you. All right, we'll start with aggregation. And aggregation is not actually one of the Gang of Four patterns. It's more of just kind of gets to the idea of why do we have classes in the first place? And so it's a great place to start. Sorry, I've got a little frog in my throat. Want to keep this real? I want to keep it close to real applications. And so I'm going to bring up, a problem statement that that customer with that wall of classes when presented to me right out of the bat is something that he needs. His company makes crystal oscillators, and they test them a fair number at a time. One of our racks, they'll test, have 40 of them going at once for an extended period of time, like days. This is aging rack, he calls it. And he's doing scans, he's just taking signals out of these things, and he wants to display the last hour of scans for a DUT that he wants to look at right now. But as I said, he has a bunch of them, okay? And he doesn't want to have a big old screen with 40 little tiny graphs on them. He wants to pull up one or two, okay? And we probably could have gone and put a database behind this and done queries off the database, and that would have been really clever. We chose not to do that for other reasons, and so I opted to solve this. I have to batch the last hour of data. So when he pulls the plot up, there's the last hour. And instead of doing a query, we're maintaining small circular buffers. Who here knows what a circular buffer is? That should be most everybody at this point, so I can kind of gloss over this a little. Real quick and dirty, circular buffers, just an array of whatever your data is, and you keep track of the place where you last put in a piece of data, and you just start putting data in. You start at index 0, and you add, in this case, your 10 points, and when you go to add point number 11, you actually go back to the beginning of the array, you go back to index 0, and you drop it in there. And so you only have your 10 points, the last 10 points, and since you know where the head and the tail of your data are, you can do a little array manipulation and reconstruct your data in the correct sequence. We do this all of the time, right? It's a common thing that we do. It's one of the first software algorithms that I learned about, and I actually learned about it way back in the day in LabVIEW graphical programming. Not this edition, this one, which coincidentally, my friend Chris knows, we know the guy who wrote this. This came out in 1994 as well. This was literally the first book on LabVIEW. It's written by Gary Johnson. It goes back so far that they made a big deal out of telling us that a 3.5-inch floppy disk was included, right? Instead of pointing us off to their Git repository where they had the code, they gave us it shipped with the disk. I still have my copy. And I was brand new to this back in the day, and I devoured this book when it came out because I'm trying to figure out how I do my career, right? And in that book, Gary Johnson gave us a circular buffer, and he stuffed it in a functional global variable. And this is it. Amazingly, I actually had a copy of this VI that went back to LabVIEW 2012. I could actually still open it. I was amazed. But there it is in all of its glory. And as a functional global, it gave us a lot of benefit. I had this great little encapsulated piece of data. It was in a VI, and the VI would show up at a couple of different places in my application, and I could put data in one place and pull data out on the other, violating data flow, which is why functional global variables are not necessarily the best solution. And I only ever got the one, right, unless I wanted to make multiple copies, because it has to be reentrant, or non-reentrant, excuse me. So that had some limitations. So if I wanted to have more than one, well, I could unpack that code, right? And this is just that code kind of unrolled onto a single block diagram. And I'd have some place where I would initialize that, and then I might have a bit of code where here's where I'm writing my scan of data as it comes in, and then there's the place where I'm reading back out at the end. And of course, if I want to drop this into several queued message handlers, I am a good developer. I'm not going to do that. And pre-classes, I'm going to package it up like this, right? I'm going to have a little library. Pre-library, it would just be a folder full of VIs. And I would have my cluster of data out the beginning there that was everything that I needed to have to make my circular buffer work. And then I would pass that around inside of my queued message handler, and I would hit these VIs as needed. But we lost something important when we stepped outside of the functional global variable, because now we have access to data we shouldn't have. Does it ever make sense to go grab the raw data array? No, it does not, because it's going to be in an arbitrary order. Okay, I've lost information there. Does it ever make sense to be able to change the head and tail indexes? In this case, we just have the one buffer index. No, it does not. If you change that, you've destroyed your ability to recover the data correctly. Now, you as the person who wrote this, you as the experienced developer, know not to do these things. Does the intern? Maybe. You hope so. Do you want to find that out when you're trying to go home at 10 o'clock at night? No, bad plan. So we want to protect ourselves from ourselves. I know Mark's a competent developer, but he might not know these things because he doesn't necessarily know my API, right? And he might give me something that I don't know. So we don't want to screw each other up. And that's what aggregators are all about. We go to this is a basic kind of guidance. If you're looking at an application that's not in classes, trying to figure out what to do, you think, okay, if I see wires and nodes like I just saw, let's go ahead and make those a class with methods. And so I take that private data and I put it in a class, and I make these methods part of the class, okay? And that's aggregation pattern. We're an aggregator. We're just aggregating our data in a certain way. So here's the class. Here's that same set of functions represented as a class. Those cluster private data, right? It's all the same data. I have the same methods, right? Here's that initialize, and that write, and that read. They're all present. This is the API that we're presented with. But we've gained, it's not just packaging. It's not just, a way to make it look pretty. We've gained some very important things here. We are now treating that data structure, that couple of arrays and the index and the this and the that, we're treating it conceptually as a single thing to be passed around. And we are enforcing the rules for manipulating the data. I can add a scan in a certain way, I get a scan out in a certain way, okay, or a set of scans out in a certain way, and in no other way. And in this way, we protect ourselves from ourselves, okay? We have protected our data integrity. We've hidden the implementation from the users. I don't know if you've noticed, that's some very old code. I've been using this code for 30 years, off and on. And I put it in a class a long time ago and forgot about what was in it. And I was working on this presentation going, it's kind of some old stuff. I probably ought to use some in-place element structures in there, right? Maybe clean up a couple things. Maybe I don't quite want to have, maybe I don't want to have the timestamp on there. Maybe I want to have it something else, right? So I can go through and I can change all that under the hood, and you never know. And all you're going to know is that I have a bunch of unit tests, because classes are really great for helping us think about things in terms of like small testable bits of code. So I've written unit tests against my class. I test every method of my class, and I can prove that it worked before I made the change, and then I can prove to you that it worked after I make the change. So you know what, I'm not a knucklehead, right? That's what we're doing. This is the things we're buying with this simple change to our code. We're buying ourselves a lot of protection. If you want to see a more complex example, last year at GDevCon North America, I did a presentation on an aggregator that I did for one of my customers, where I had a bunch of objects that I needed to, store in a repository, and I wanted to be able to search for subsets based on certain keywords, right? It was my variable repository. You can find that online. Go watch the video. That was just a cool thing that I did, and I thought it was neat, and I shared as another real-world example I saw for a customer. So this is a block diagram with one of those aggregators in it. It's nice, it's simple, it's clean. I've replaced a portion of the queued message handler's private data with just this little object, and I can carry that around and I can act on that as I need to, right? I don't have a whole lot extra that I'm looking at, which is actually I find it to be a bit of a distractor anymore. Even better, and this is where the syntactic change starts to affect our thinking, because now I truly am treating that complex array not as an array and a pointer, but as just a unit entity. And I can decide I need to do things like add two of my repositories together. What does it mean to add them? I can do all of that, and it's just a simple thing. Take this one and this one, put them together. Like we have the functions for the waveform data type that will add two waveforms together, right? We're just taking them, put them together. We know what that should look like. We can write a function for it. Sets are another example of aggregators. That one comes with LabVIEW. It also comes with setMath, right? What's the intersection of my two sets? And we can just do that and change it as needed. And we can build on that. Once I have these sort of new data types, I can make more complex data structures. I can make another aggregator, for example, that has several aggregators in it. Another customer, I just did this a few months ago, needed to have a table of string data of a fixed size, right? Because he had he had a logger that was displaying logged test steps, and the original developer didn't realize he was going to run for 4 days straight and like fill up his memory with this buffer. So I made him a string buffer of 2D array of strings, fixed size, and I made it out of a table buffer, and there's a symbols buffer because it went into a multi-column list box with checkboxes in the front and stuff, and that's actually like a couple of different of these circular buffers put together into something more complex, right? So here's that sequence log circular buffer. It's got a read and a write. Those are what I exposed to you. I'm just accessing these other circular buffers. Another example of an aggregator. We just released back, sneaking in a little bit of a self-plug here, just back at GDevCon NA back in July, we just released the actor hierarchy inspector, which is intended to replace MGI's monitored actor. And I have to keep track of all the actors in a system and display that tree to you. Shockingly, there's an actor aggregator under the hood that stores all of my actor information to make it easier to manipulate. So these things come up all the time. It's just a basic thing that we do. So, another pattern. This is one of my favorites. I got to hydrate again here. This is one of my favorites. This is one I use if I haven't used it. I've got 2 projects this year that I haven't used it on because we haven't gotten to it yet. Every other project I've worked since I left NI in 2017, I have a state pattern somewhere in it. It's such a useful pattern. Basic problem statement. This is customer of mine had it happened to be PLC. I'm showing a compact Rio here because this is a LabVIEW event. But we had to control this PLC. And so there was a software representation of all the things we wanted to do with this PLC, at the higher level, at the logic level. It happened to be an actor framework actor. I'm going to show it here as a queued message handler to show how it's relevant in a non-class environment. So what kinds of things would I have to do? I had this queued message handler, right? And I would have to do several things, like I might call my initialization case and connect to the instrument. It's the first thing that I would do. And then the instrument would report back that I had successfully connected to it and it had acknowledged the connection. And so then I would tell the instrument prep to run, which was essentially move a bunch of stuff to where it needed to be, clear your throat, so we're ready to actually start moving products around. But don't. That would be a terrible thing to have happen in the middle of a run, so we wanted to have some guards. Only do that if we had been disconnected, right? And so we had to introduce an enum that represented our current operating state. And then we put some guard code in the connected case, where if we're disconnected, we'll do that prep to run, otherwise we'll do nothing. Right, it is nice and large. A little later on, we're going to get, the PLC is going to tell us, we're going to get the return to slot message. This is the PLC telling us that a test article has come back and needs to be put away. So go do that, but you have to be in the ready state for that. Oh wait, what's the ready state? Oh, okay. So there's actually, like, after we've prepped to run, we'll get a report back, and that puts us into a different state, unless maybe something else has happened. And you see where this is going. We keep adding guard code and all these exceptions, and you can do it and you can manage it, but your queued message handler is going to become very complex. That one diagram is going to get bigger and bigger and bigger and bigger. And you can do that. And in fact, the trigger for this presentation came out of a presentation that Norm Kirchner and Darren Nattinger gave at GDevCon NA back in 2021, where Norm Kirchner was showing how you can do this in a traditional queued message handler. And he calls it top-level baseline. And it looks like this in all of its glory. I mean, I don't have anything populated here. This is just the template. But this is just the template. Okay? There's a lot going on here. It's a big diagram. Okay? I personally get distracted if there's too much on my block diagram. I want to drill down to the important stuff. And that's where state pattern can help us. And normally, there's a lot of convolutions going on here. State pattern simplifies this. What state pattern says, what state pattern is intended to do, is, given an object of some kind, in this case, our queued message handler, we want it to, if its internal state changes in some way, we want to get different behaviors from the same set of messages. I send you a message, and you do one thing, and then you change your state. I send you the same message, you do something else. Okay, you've appeared, it's like I have a different object at that point. There's the UML for what it looks like. There's a context, which in this case is a queued message handler. Could be any of our flavors of actors. Could just be another class. If you think about DACMX, it has internal state, right? Any context can have internal state. And what we're doing is we're changing around these state subclasses, and I'll show you how that works. So how do we get there? What does that look like? Here's my construct, right? And we're playing off of a basic idea of we've got, I wish I had a laser. We've got our state enum, right? Disconnected right there. Maybe over here we're checking the disconnected case for it. That state enum has one job and one job only. Its only function is to tell me what to do with the rest of the data in my cluster here. Okay, I'm going to do different operations on the same set of data. Now, if you're looking at an application, you're thinking of refactoring. It's my other target audience, is you're trying to figure out how to refactor older LabVIEW code. If you're looking at something trying to refactor it, that's a big flag. Anywhere you see that, the question I would like you to ask yourselves is, can I replace that cluster data and that enum and that case structure with a class and dynamic dispatch VIs? Okay? So again, I took the internal cluster of the queued message handler, I put it in a class, and every place where I had one of those case structures that keyed off of that enum, I've replaced it with a dynamic dispatch VI, and the class that's on the wire will tell me which one of my cases to do, which one of my methods to call. That's how state pattern works. Okay? So, for the project in question, I made something called FE-base. The front end is what we call the thing, and this was the base state. And the base state, all it does is carry around your data, most of your data. You might have some data in your subclasses. Most of the data gets carried around in there, and then in addition to that, I define all the methods, all the things that I can do at various times. Okay, and so then I'm going to. So here's that class again. You know, some of my methods. There's prep to run, and there's store rod. Those are my two methods, my two dynamic dispatch methods, where I want to do something different depending on my state. So now I make two child classes, one for idle, one for ready. And you'll notice that idle implements prep to run because prep to run is only valid in the idle state. Ready implements store rod because it's only, you know, we can only store rod if we're ready. And we have maybe a couple of other methods where we do something, but we do a different thing depending on our state. So the queued message handler structure look like this. When I first come in, you know, idle is the object on the wire, on the class wire. So when we get that init message, which is just our starting up condition, I'm going to call my entry method. Okay, I'm going to call entry every time I'm init. When I'm in idle, idle implements an entry, and that's what I go connect. Okay. A little later on, I get prep to run. Well, I have a prep to run method in idle, and so there we go, right? I do the stuff, whatever the stuff happens to be. If I get the return to slot, well, I don't have return to slot. That's only defined at the base level and in another state, so I have nothing to do here. I don't do anything. Now the question becomes, how do I transition? How do I go from having idle on that wire to having the ready state on that wire? Right? I have to have a transition method. In this case, it's called go to ready because that's what I want to do. How does that work internally? Question for you guys, and just shout it out because I'll echo back what the answer is. Here is the connector pane for the base version of go to ready. It is a dynamic dispatch VI. Anybody notice anything interesting about that connector pane?
I believe you have superclass as output.
Yeah, so it's dynamic. So Mark called out that only the input is dynamic dispatch. Andre's saying that my output is just the base class. That's absolutely true, right? It's not dynamic dispatch. What does that mean? That has a specific meaning to the compiler. Yeah, that's what's going to happen. Yeah, Andre's getting ahead of me, saying that that's where I'm changing class internally, and I can. Let me show you how that works. The way that works is this: if the input and output are both dynamic dispatch, I am declaring to the compiler that the specific object going in is the same object coming out. This is where the differentiation between class and object really starts to matter. You know, at first you're like, why are we differentiating? And we get sloppy in our language, but it actually is a critically important distinction. And here's where it comes into play. The specific object in is the specific object going out. And the compiler, you will notice, enforces certain restrictions on what you can and cannot do with the wire from input to output. Okay? Now, do I have to have the output at all? No, I don't. I can have nothing coming out. I can just wire it in. And what I'm telling the compiler is, here's an object that you don't have to return to me. And so you can do whatever optimizations you're going to do, but you're not returning this to me. When I have this arrangement, what I'm telling the compiler is, that's just data coming out. And it doesn't have to have anything to do with the object that came in. It happens to be the same parent class. That's a coincidence. That allows this behavior, as Andre pointed out. Thank you. Idle comes in, ready goes out. That's a legit construct. Now, we're not done. Okay? Idle has useful attributes. I showed them to you. They might be things like, you know, the queues of other queued message handlers that I want to talk to. Kind of want to hang on to that information, right? That's just the default values. So I need to transfer data from idle to ready. And so I introduce a VI here, and it is a dynamic dispatch VI called swap attributes. And swap attributes, I just do that. This works, by the way. You can do this. This is kind of cool. you can access, in a VI, you can access the private data of 2 instances of the same class as long as that they're sharing the method there. So this is valid construct too. But I just go grab all my data out of the old class and I put it in the new one, and I'm good to go. Now, there's a bit of a hazard here. There's an easy way to make some bugs, which is that if you take out an attribute, you decide you don't need it anymore, you'll get a broken arrow here, a broken wire, and you'll know to go fix it. But if you add one, you don't get any helpful clues from the compiler, and you'll not transfer the data, and that kind of sucks. So our recommendation, pro tip, if you will, is to take all the attributes that need to persist, put them into a cluster inside of your cluster of private data, and then when you do the transfer, all you do is transfer that cluster. And so if you put stuff into the cluster, it'll, the cluster changes and things mutate the way they mutate, and you'll be happy, and you will save yourself that runtime bug. And I'm embarrassed to say that I wasn't the first person to think of this, but this is a really clever idea. Right. So now I know how to do a transition. Everybody's clear on that? Now I have transitioned. Now what's on that wire is ready, not idle. And so when I get the store rod message, now I know what to do, and I go do it. Okay? State pattern is awesome. It conceptually saves so much energy. Your block diagram gets simple. Your message handler is about the messages, and your state classes are about the things you do in response to messages, so you can think about one and not the other. The states are in their own partitions. They're their own things. They are individually testable. You can take a state class and test it outside of the message handler. Okay, so you don't have to send it a message. You can just call the VI. And if you have to add a new state, I had to add this nest inhibit, which was a response to an error condition. I had to change my behaviors again. I made the state, and instead of having to go through 47 places and change the case structure, I made the state, I put it into the system. I had to create, obviously, the go to nest inhibit. That was the only method change that I had to make in the parent class. And then it was just done. Now, going back just a little bit, a lot of people will tell me that they really, really like, one of the things they like about top-level baseline is being able to see all of that code, ignoring the fact that they have to flip through case structures, but they can see all of that code on the one block diagram. Well, okay, I'll buy that up until about 2019, because in 2019, 4 years ago, if you double-click here, you get a dialog box comes up. And that dialog box will show you the block diagram of every VI that could possibly be called at that point. And you can flip through them really, really simply. And the diagram is actually semi-live. You can click through the cases in there. So you have all the visibility you need, but only when you need it. Okay? My instrument controller ended up looking like this. My context was an actor. We have a different way of doing this in Actor Framework that's similar, that there were a variety of reasons why we couldn't do it in this case. We actually went with the more classic structure, which is what this is. But there's my context, there's my state class and the child classes, right? And then there's this guy, the state object, which is what my FE base actually inherits from. What is that? What's that about? Well, that's my next favorite design pattern, template method. Template method solves another problem. Let's go back and look at all the possible things that I might need to do, with my state pattern class arrangement here. I have several things I have to do. Some of them are very transactional, right? I'm going to be getting, this connected message. I'm going to be getting return to slot over and over and over and over and over and over again, right? Some of the things that I need to do, some of my messages are transitional. I'm going to go from idle to ready. Some of the things I want to do are things that I do in response to a transition, right? So, I would like to, when I enter idle, I would like to try to connect. Okay, that's a thing I do once in a particular state, and not necessarily in response to a message. So, how do we resolve that, right? There's things we want to do. When we transition, we always swap attributes. When we transition, we want to invoke this entry state or an exit state if it happened to have one, okay? There was an actual algorithm for how we go from idle to ready or ready back to idle, okay? We want to do a set of exit operations, always. That's defined through dynamic dispatch. Every state does something different to exit, but they all do something. We want to swap attributes. May actually look a little different depending on the state we're leaving, the state we're entering. We may actually use a state transition to discard some data, okay? Entry operations in going into the new state. I'm entering idle, I want to connect. That's an algorithm for stuff we want to do. We do this over and over and over again. We don't want to replicate this code on every single transition, so we put in a VI. Okay? The change state VI. And that's what this parent class is about giving me those definitions. So here's change state, here's entry, here's exit, and swap attributes. Change state is not dynamic dispatch, the other ones are. This is template method. My flippant subtitle for the design patterns book is that thing you've been doing all this time. It actually has a name. This one happens to be template method. I give you an algorithm. I give you the skeleton of an algorithm. We're going to do certain things in certain order, but I'm going to let you, the designer of my subclass, define for me what those specific steps are. I require an order of steps. You get to define the steps. State object is a piece of reusable code. I've used some variant of this for several years now. I don't have the one I only have the one that's for actor framework, but if you download the one for actor framework, NI-state pattern actor, you can change that to not inherit from actor and you're good to go. But that's what template method is. That's an example of it. Another example, another one that I do all the time, the crystal oscillator customer. We've got a big plug-in architecture for generations worth of very expensive instruments. And they all, we stand them up as objects in our system that move through various templates in our system. One of the templates they move through is how do we configure them? How do we recover their configuration from disk? There's an algorithm for that. The algorithm is go check, in the first specified location, go check for a config file. If the config file exists, deserialize the config file in the manner specific to the instrument. So there's my dynamic dispatch override. If there's no config file, go find the default config file that we store with the class. Okay, it's part of my algorithm. If it's there, go do what you do and deserialize yourself. You know how to deserialize yourself. And if that fails, we'll warn the operator. Another example of template method is, of course, the actor framework. Actor.lv class is one big template method. The lifespan of an actor has several touch points where you, the builder of the actor, can change the actor's behavior. Pre-launch init, actor core, how you handle errors, how you stop. These are all things you can change in how a specific actor works. Cool, I'm doing great on time. So that's the three that I suggest, if you're just getting started, that you investigate and look at starting to use. I'm going to mention a fourth. This is not one you start with necessarily, but it tends to fall out if you're starting to do things like I'm injecting classes into my system somehow to put them through my template method. That's the question, right? I've got template methods around. How do I get classes? How do I get objects to put into the templates? Well, with state pattern frequently, or in certain instances with this customer of mine, if you're doing, say, instruments, you might give the user a short predefined list of instruments, or you have a predefined list of states, okay? And they go and pick them, and you go instantiate them, and it's hard-coded and everything's statically linked. That's an example of a closed set. You know how many you have. It's not that many. It's okay. Very often, especially if what you're talking about is hardware, we might choose to do that dynamically. Most of you, I think, know that you can go create a default value for a class from the class file on disk and inject it into your system that way. And it looks like this. Factory pattern comes in when you decide, okay, I've made the system and I'm doing this dynamic injection, but maybe I want to test that piece of code and therefore I want to use a closed set of mock objects instead. I don't want to go through the load process. I don't want to add that complexity to my testing, right? I want to be able to swap them back and forth. Okay, we can do that. We can make a class, an interface type class, factory class, and we give it a method called getInstruments in this case. And then we make two children. One is the closed set factory, which does my closed set. One is the dynamic loading factory, which will go and get them from disk. Okay, this is factory pattern. Now, factory is just a parameter, and I get to pick and choose. And I can do that. I can do that for testing, or I can do that because I've got some reuse code that I'm applying to a different circumstance. But factory method just says, define an interface for creating an object. Let subclasses define how we actually do the instantiation, or what classes we instantiate, okay? It looks a bit like this. So I might have my app would take as an input, where am I getting my source objects? And then inside of my application, I have the VI, this go get instruments, and go get my source objects. Gonna wrap up with just mentioning a couple of other patterns that you might want to go investigate on your own time. My configuration objects, the ones that I use to give me ultimately my configured instrument, those are examples of mementos or tokens. Okay, so that's basically just the configuration for an instrument wrapped up in a class, and I can handle those as a set and deserialize all of them. It's an example of a token. Undo is typically written with mementos as well. Proxies are another one of my favorite and are very, very simple. You can have a remote proxy, which is just I have a class that is the same API. It has the same API as a local class, but it actually just covers for a remote connection. Or another great use of proxies is I have a resource like, I don't know, the reference to a VI, and I want to give it to Mark, but I don't trust Mark with the reference to my VI, so I'm going to put that reference to a VI inside of a class, and he only gets 2 or 3 methods because those are the only things I want him to be able to do with my VI. I see you sitting there, Mark. Yeah. Yeah, I know. I know you do. He wants my reference. Sneaky bastard. I love you guys. I really love you guys. Decorated patterns, another one, which is essentially I have a class with an API. I make another instance. I make another child of that class with the same API. I put the first class in the second class, and I can add functionality to it. I'm not going to go into the details on these. These are examples for further reading from here. Or if you find this one too dry, I'll be honest, it kind of is. If you find that one too dry, you might check this one out. There are lots of books on design patterns. They're all just presenting the same content or similar, but in different ways, and so some of them are more accessible than other ones. I have not read this one. Sam Taggart, if you know him, recommended this one to me. I need to get to it. His book recommendations I have found to be solid, so I'm passing this along to you. We talked about 4 patterns, 3 that I'd like to see you start using now if you're not currently using classes, 1 that you should know that's coming, and these are the contexts in which we found them. I will assume you can read, so I won't read the slide to you. In fact, I will recover the time specifically for questions, and I think I've got about 2.
Yeah, I reckon we've got that time for 1 or 2 quick ones.
All right, well, find me later if you want. Oh, wait, I think. Mike's right there.
So there used to be a really nice reference on the communities applying common object-oriented patterns to LabVIEW. It seems to have stale, I think.
Yeah, they were working on that when I was at NI, when I first came to NI. And
it was very nice at one point.
Yeah, I think the folks who were working on it moved on to other projects, and it wasn't complete either. It would be lovely to see that resurrected. Maybe I'll go find that and see if I can work on it. In my vast spare time.
Hey, Alan. Thanks for the great presentation. Just further to that, Sam Taggart and I went through the Gang of 4, and we have LabVIEW example code on all the Gang of 4 design patterns on GitLab somewhere. I've not looked at it for a few years, but I'll send a link in Discord.
Yeah. Can you go recover where somewhere is and post that?
Yeah, we'll do.
Yeah.
Okay, guys, anything else? I think we'll pick up in Discord if that's okay. Thank
Right
you very
then.
much, Alan.
Thank you all.